Hello, my name is Noah Bewley, and this is my video for Lab 3 for 2212 Physics. This first slide is just the basic concepts and equations used in Lab 3. I know the text is a little bit obscured. Something weird is happening with the formatting on PowerPoint whenever I go to record this, but the text it's obscuring is just describing what that equation is. Of course, that equation is the Biot-Savart law, which just dictates the magnetic field produced by a magnetic dipole, in our case specifically a bar magnet. Below are just the simplified versions of that. So all it says is that the magnitude of a magnetic field on axis can be just set equal to k, which is representative of constants, mu naught over 4 pi, um, and then also constants related to the magnetic dipole times r, the distance away on axis from that magnet, raised to some power. And if you just take the natural log of all of these terms, you can wind up with a linearized plot, which we're going to use later when we gather data and use Excel to find the value of n. Experimental setup. The first part just involved aligning the y coordinate of the magnetometers on our phones with the magnetic field of Earth, essentially negating the magnetic field of Earth from from our measurements. The magnetic field, if it's aligned with y, has no effect on the x-axis, which is where we were taking all of our measurements on how the bar magnet was affecting the magnetometer. And then in the later part of this experiment, where we do an off-axis measurement of magnetic field, we have these tabulated data of the magnitude of Earth's magnetic field in our particular location in Atlanta, Georgia. Um, Using that tabulated data, we can basically negate Earth's magnetic field by literally subtracting it out from the observed measurement, knowing its direction. And then through obtaining on-axis pairs of magnitude versus distance data, so basically moving our phones around and changing that distance and observing the change in the magnitude of the magnetic field based on that distance change, we get these data pairs. And then using the logarithmic linearization seen on that previous slide, which is just the natural log of uh, the simplified equation, also on that last slide, we can easily just take that plot and plotting ln of k versus ln of r, we can find the slope n is equal to, experimentally I found that it was equal to negative 2.6, which is different than the expected negative 3 proposed by the Biot-Savart law. The most likely reason for this difference is possibly some other interfering magnetic field, whether it be from electronics or some charged metal around. And we also can easily find mu for this bar magnet using this equation off to the right that relates the magnitude of the magnetic field to mu naught over 4 pi, which are all constant. And if we know r, basically using a measured pair of the magnitude of the magnetic field and r, we can easily solve for mu. And I got it was 2.3 amps per meter square for this particular bar magnet. Here's just a little snapshot of the Excel data and the linearization we used to find r. This is just a photo of my glow script. All the glow script was doing was a direct application of the Biot-Savart law at 6 points, 2 on axis, 4 perpendicular to axis, and some at 4 degrees. This is just a visualization of that. The on axis are the orange, the perpendicular are the teal, and 45's up there, that pink. These are the results comparing the off-axis theoretical produced by GlowScript and the off-axis observed. We saw that the observed was a higher magnitude than the theoretical by about 85%. The reason for that is most likely, again, interfering magnetic fields that were additive in this case and kind of overinflated the value we saw during the. These are the true statements it asked for from the lab instructions. The true statements of those four were from when the magnetometer is far away from the magnet, we see a near zero magnetic field. This is because the magnetic field magnitude decreases with respect to 1 over r cubed. So as you get far away, that magnitude of magnetic field drops rather quickly. And as it moves closer, the x component of the magnetic field increases for the same reason. This is the what if discussion. So what if magnets were oriented end to end in the experiment? Well, we would see maybe not necessarily a doubling of magnitude based on distance, but because we have more magnets producing magnetic field, we would expect to see a proportional increase in the magnetic field at all distances r due to that second magnet. And what if there was no compensation for magnetic north? Well, we would have these skewed measurements that would basically propose that the bar magnet was producing either a greater magnetic field than it actually was, or a lesser magnetic field than it actually was by a factor of Earth's magnetic field. And that's it. I'm done. Thank you for listening.